Okay, in this lecture we are going to review the electromagnetic spectrum that I quickly showed you in class today, which I'll review again tomorrow, and talk about some of the governing equations that we've learned so far in atomic structure in terms of quanta, energy, discrete energy levels, and all the things that we've been talking about leading up to the Bohr model. Okay, so we have shown right now is the atomic spectra, and I'm showing you a electromagnetic spectrum, so to speak. And if you notice, this is the frequency. And if I was to draw on here, and I'm going to, um, and I notice that cosmic rays and X-rays, and there should be gamma rays in here, have the highest energy. And we learned that energy is equal to Planck's constant, which is a value that tells me how energy changes discriminately, meaning it changes in bundles. Okay, it's not a smooth continuous. There's an actual integer that energy changes by. It's not a continuous flow. It's a step by step, let's say on a ladder. And those steps, or that value between steps, is exactly what that Planck's constant is. So in any case, it's times that by something called the frequency. We learned today that the frequency is how often we will have a wave, okay? How many actual wavelengths, and this would be one, okay, and how many wavelengths in a certain time period, sometimes called a hertz, which is the same thing as a cycle per second. So over a second is a frequency, how many, or per second. And that cycles could be many. When it comes to waves, it's how many wavelengths per second. Okay, and you can see that I have 1, 2, and approximately 3.5 waves here. Any case, so if I was to draw on this, you would see that the frequency is low on this side of the spectrum because the wavelengths are high. But as we go across, as I can try to draw, the wavelengths get smaller, okay, because the frequency has to increase, okay, incredibly. All right, so we learned that a wavelength is equal to the distance between one sine wave and another, okay, or one wavelength. So this is exactly one wavelength. We use lambda symbol to measure, okay, what in fact a wave is, or one crest to another positive. So the start of one is the positive, the negative, start of another, that distance is a wavelength. Now, radio waves have incredibly long wavelengths, and they have low energy. Why? Well, because their frequency is low. The frequency picks up how many wavelengths per cycle, or per second, or per time period increases as the wavelength gets smaller. So this is one governing equation, and that's how energy is related to the frequency. But we have another one. Speed of light is how fast these waves actually travel in. And the speed of light is equal to the size of the wavelength, that's going to be in meters of some sort, times the frequency. So this is an inverse relationship. So as I was trying to say before, as the frequency increases, we're over here now, lambda, the size of the wavelength, has to decrease, and it's equal to the speed of light. And of course, as we're on this side of the electromagnetic spectrum with radio waves, well, the lambda, the size of the wavelength is huge, so the frequency drops. Not many per time period if the wave is big, and that should make some sense to you. Okay, and this value stays the same if that's all true. So that's the theory behind that. And notice we have radar, FM radio, communications, cellular phones, microwaves, infrared, that's basically thermal energy. And then we have this small sliver right here of visible spectrum. Even the light, the colors we see are part of that spectrum. And if you were to basically take this part right here and make it bigger, okay, zoom in on that little sliver, we can see that actually light is broken up into different energies or wavelengths. Now here we're looking at angstroms. Angstroms are 10 to the 8, okay, negative 8 I should say, okay, and nanometers are 10 to the negative 9. So nanometer is a billionth of a meter. Okay, you notice here is the meter here. Any case, that being said, All right. Um, sorry, nanometer. I might have misspoken here. So going back to these measurements, 400 nanometers, okay, is 400 times 10 to the negative 9 meters. So if you notice, that becomes 4.0 times 10 to the negative 7. These are the same numbers. So I'm just showing you how these numbers are the same. Okay, it's getting bigger by 100, so that number goes to a negative 7. All right, if you go that way. Any case, look at this. This is my Roy G. Biv. Red, orange, yellow, RG, Biv. Now we forget the indigo here, but there it is. So red, as we talked about today, has a now, of course, this is actually flipped on its head, unfortunately. Red has a shorter wavelength. Look at that, 700 nanometers. I mean, sorry, longer wavelength. And the violet has a shorter. So in essence, this thing is flipped. This is actually a bad drawing for me. Notice I have the higher energy, higher frequency waves over here. So this whole chart should be flipped around, where we should have violet over here and the red and the infrared on the same side. But I hope you get the point here, that we can break this color's light into higher energy. Okay, shorter wavelength, or longer wavelength I should say, lower energy. Okay, smaller wavelength, okay, higher energy. Why? Well, if you solve for C, C is equal to lambda times the frequency. If this is a constant value, so again, same idea. If I have a smaller lambda, higher frequency. Okay, that should make sense to you. So the wavelength is increasing. Okay, it's getting longer, and here it's shorter. And of course, the frequency increases. All right, so enough said about that. Now, some constants that will always be given to you is the speed of light and Planck's constant, but this is not written right. This is joules second. Okay. All right. So what's the frequency of violet light at 400 nanometers? I don't know the frequency. Okay. Well, I know that C is equal to a lambda times frequency. Okay. That's one of our governing equations. So I'm going to solve for frequency. So rewriting this, I get frequency is equal to, algebraically, C over lambda. Okay, now C, or speed of light, is 3.00 times 10 to the 8. That's meters per second. Okay, we'll put the second here. And we're going to divide that by lambda. Okay, 400 nanometers. But you should notice something, okay, that this is in meters per second. This is my frequency. I'm sorry, my speed of light is a velocity of meters per second. I can't put nanometers down here. It won't cancel. So I've got to convert. So how do I do that? Okay, well, very simple. We've been converting all year. 400 nanometers. And a nanometer, like I said, is a billionth of a second. 1 times 10 negative 9. I want to get rid of nanometers, so there it goes. I want meters. Okay. Well, for every, this is a bigger unit, smaller number, right? So for every 1 meter, I have a billion. 10 to the 9 nanometers. Now, some people are bothered by that because they know that a nanometer, okay, is equal to 1 billionth of a meter. But look at that. That's the same thing. 1 over 10 to the 9 is the same thing as 10 to the negative 9 meters. Okay, but there's what? A billion of them. That's why that's not a negative number. Okay, there's a billion of them. Just like if you're doing a milliliter to a millimeter to a meter conversion, there's 1,000 millimeters to 1 liter, 1 meter. Okay, so in any case, nanometers cancel. Okay, and I'm left with dividing by 10 to the 9. Okay, so you take your calculator to your 400. Okay, times 1. It's a hard one. Divide by, I do second function, EE, and I do 9. E to the 9 is the same thing as 10 to the 9. Okay, no caret key if you don't have to. And I get an answer that says 4 e to the negative 7. That means 4 times 10 to the negative 7. And that's the way you really should write that. So I write that in there. 4 times 10 to the negative 7, which looks a lot familiar to what we just saw here. 4 times 10 to the negative 7. Ooh, we did the conversion. Ooh la la. I'm so tricky. All right, so continuing on. Let's get rid of some stuff that's in my way. Now let's go find that value. All right, changing colors because you know I can. All right, so now we're just going to take, since I already have 4e to the negative 7 in my calculator, I'm going to divide by 3.00, second function. I'm going to put to the 8, second function EE. Okay, I already messed up, second function EE to the 8. Okay, I'm plugging that in. And I get a funky number, but I'm just going to do the x to the negative 1 key. And I get, okay, 7.5 times 10 to the 14. And my units, well, this is meters. I should have left that there. So gosh darn it, meter over meter cancels, and I'm left with 1 over second. So my answer is 7.5 times 10 to the 14, and that is second to the negative 1. That's another way of saying 1 over second. Okay, all the math you learn in this year, maybe, who knows. And that, my friend, is your frequency. And a frequency is per second. That's how many wavelengths per second. And by the way, this is also called a hertz, a per second frequency. So that's how that worked. A couple of conversions here. The math really isn't that difficult. Okay, now what's the energy associated with blue light? Now let's go find some blue light. We're going to need some wavelengths here. Blue light, okay, and again, I didn't give you a nice number. So let's take a number between green and violet. Okay, let's make this, okay, 450. Okay, I know you could pick any number. This wouldn't be like a test question, but let's use 450. Okay, between 4, we're going to get something close to blue. All right. Any case, so 450 nanometers. All right, so we have 450 nanometers from my chart read, and that is the wavelength, how long the wavelength is for blue light. Okay, now what's the energy? Well, I know that energy is equal to Planck's constant times frequency. Now, I could go into this equation here, plug in my lambda that I just found, and using speed of light, I can solve for V and then put it back in. Or I can combine these two equations. How do I combine these two equations? Very simple. Let's change the ink because I can. And I know that frequency from this table right here, frequency, if I rearrange it, is equal to C over lambda. So I can just actually plug this in for frequency right here. My gosh. So E is equal to Planck's constant times C over lambda. Let me just rewrite that because I know you can't see it. So energy is equal to hc, Planck's constant, times speed of light over the wavelength, lambda. And now I don't have to do a two-step problem. Okay, so let's do that problem. All right, so let's plug that in. So we have Planck's constant, which is given to you. I'm going to write this down here because we have the room. And it's 6.62 times 10 to the negative 34. That's a huge, small number. Joules second. Okay, I can see I'm running out of space. And I'm going to times that by, let me just redo this because I want you to see the units. Okay, so let's redo it and let's change the color because I can. Okay, so 6.62 times 10, looks like I'm doing a better job of predicting, negative 34 joules seconds. Okay, that's my Planck's constant. Speed of light, also another constant given to you, 3.00. You should know this one by heart eventually. 10 to the 8 meters per second. All over the wavelength. Now, look at this. Meter is in here. You can't use nanometers. So just like we did here, we're going to have to convert. So you probably can guess, because 400 became 4 times 10 to the negative 7, 450 will become 4.5 times 10 to the negative 7 meters. Okay, if you don't trust me, do the conversion. Stop, go back and see how I did the conversion. You'd come up with the same number. Okay, so things cancel, party people. And here we go. Seconds go bye-bye. Okay, meters go bye-bye. What am I left with? Good old-fashioned energy, which is joules. So what we're trying to solve for in number 2. So let's put this in our later of calc. And we have, here we go, 6.62 second function, EE to the negative 34. We're going to times that by, again, if you don't use the caret key, you don't need all these things, you don't need all these parentheses, but do whatever you got to do. 3.00 second function EE to the 8. I'm going to hit enter for fun. Then I'm going to divide by 4.5 to the second function to the negative 7. Oops, I forgot second function EE. Okay, and then negative 7. Hold on, I think I made a mistake. No, I'm good. Negative 7. Yep. Okay, and I get, whoa, a tiny number here. Okay, but it's the right number. Let me change my ink. Not because I can. Okay, I gotta stop staying at 4.41 times 10 to the negative 19. And that's joules, because everything cancels. Use your units, people. Of course, that goes up here. Now, this is actually joules per photon. Okay? Each individual packet of light we learned. So it's a small number. This is a one particle of light. So obviously, it's going to be tiny. Okay. So back to the last question. What's the wavelength of light? There's a frequency of this. So we're giving the frequency to equal to 6.38 times 10 to the 14. And that's s to the negative 1 right here, so that's 1 over second. And they want the energy of the light. Well, that's an easy one. Energy is equal to Planck's constant times the frequency. So let's plug that in. Planck's constant, 6.62 times 10 to the negative 34 joule seconds. And we're going to times that by the frequency. Well, no, we'll just erase this for fun. Put these together, times this. What do I get? And I get my seconds. This is a second, really. That's going to cancel. And I'm left with joules. And let's go find that number. 6.62. Okay. To the negative 34. All right, times 6.38 second function, okay, EE to the to the 14. All right, and now I have, if I did this right, amongst the noise in the hallway, 4.22 times 10 to the negative 19. A lot of small numbers here, a little cumbersome that way, but make sure you use your units. Okay, not really that hard, which we see what we're doing here based on the philosophy of frequency, energy, and wavelengths. Okay, so this is equal to our energy. It's in joules. We got joules here, and again, this is a joule per photon. So each packet that's carrying this frequency of light, it gives that energy exactly. Okay, what's the color of the light? Last question. Well, the color, wow. Well, I can't really use the energy, but what I can do is turn this, okay, frequency into a lambda that I can look at, okay, some color charts here. So the governing equation is speed of light is equal to lambda times the frequency. And so I'm going to solve for lambda. So the wavelength is equal to the frequency, which is 4.41 times 10 to the negative 19. That's joules over my lambda is, no, I did that wrong. Feel bad, now I'm over it. Okay, so for those that followed and said, don't do it, I didn't, thank you. Okay, so if I rewrite this, lambda is equal to speed of light over the frequency, right? That v goes to the bottom. So my speed of light is 3.00 times 10 to the 8 meters per second. And of course, my frequency that was given to me in, well, that was given to me in the problem, and I was writing this one, okay, is 6.38. So I was wrong for two reasons. 1 over a second. That's my frequency. Okay, and you can see that the seconds will go by the wayside, and you're left with just meters, which makes sense. That's a distance. So put this in your calculator. I have 3.00 second function e to the 8 divide by 6.38 second function e to the 14. All right, and I get a magical, probably not magical, 4.70 times 10 to the negative 7, and it's meters, okay, or 470 nanometers, converting it to nanometers. So let's go back up. Let's get 470 nanometers. So 470 nanometers, we are somewhere between green and blue, okay? So is that turquoise? Is that blue? Is it green? Blue, green, assuming I made no mistakes, okay? Let me just make sure I use the right number since I've got a lot of stuff going on here. 6.38 is my frequency, speed of light. Yeah, it looks like I did everything right. Here it was this times this, so I got 4.2. That's the energy. Yeah, looks like I did everything right. Okay, so that's it. 470 nanometers, and that would have to be somewhere in the range of green. Okay, don't know exactly, but somewhere in the form of green or blue-green. And you wouldn't be expected to know that. Okay, so I hope you followed this. It's a little cumbersome in terms of the smallness of the numbers or the largeness of some of the numbers, but the equations are very simple. Okay, see you in class tomorrow.